So we're not doing any math today. We're setting that aside. But it's very much visualizing what's going on at the molecular level that we can't exactly see. Okay? So I have an example. Oh, shoot. Let me get the volumes on in my recording. That's the worst when I record the whole lesson with no sound. Okay. Good. So last time we mentioned the idea of a collision, right? In order for a reaction to happen, things have to collide. If they don't collide, there's no chance of a reaction. Okay, they physically have to hit each other, right, for it to happen. But, as we're going to look at today, just because things collide doesn't mean a reaction occurs, right? Otherwise, every time you stepped on the ground, a reaction would happen, right? Because they're colliding, right? Just like the world would fall apart if that were the case. Okay? So as we look at collisions here, let's get a little more detailed, okay? So here's my chemical reaction that's going on. Look up here, everybody. So we have this NO molecule, which is this, okay? It's reacting with an O3 molecule, which is this one, to make NO2 and O2. So in order for this reaction to happen, they have to collide in the perfect spot where the O that needs to bond here can attach and have enough energy to break the bond there, right? Because that's how these can become these, right? Do you see that? How like this red is now being bonded here? Yes, Cameron?
What would happen if the oxygen molecule of the nitrogen oxygen thing collided with the ozone? Like, would the reaction occur, or would it just, like, not?
Depends. So sometimes, if it doesn't hit where it's supposed to hit, then it's just bumper cars, and no reaction happens. Other times, you make a side product you weren't intending to make in the first place, and you get these other things that are made that wasn't like the intended goal, which we'll kind of talk a little bit more as we keep going. Okay? All right, everyone visualizing this idea of a collision? Yeah?
Is there ever a time when, let's say, both of the oxygens from the ozone tried and both at the same time try to form the NO2?
You're saying, say that one more time?
Like the NO from the ozone, both of the outer oxygens try to go off and form the NO3 at the same time.
Oh, and make NO3 instead of NO2? It's possible, once again, like probability game. The reason why things turn into products is because it's a more stable arrangement than it was before, at least the majority that's made. So if it's not turned into something more stable, then it's likely not to happen a whole lot. It still could. You get some random byproduct, but like the majority of your product would be the other thing. So, all right, I have a visual here so we can connect our whole triangle. So I'm going to do a reaction for you, which is this. Okay, so I have some methane gas, okay, which is what comes out of our gas line. So imagine a whole bunch of these little guys are coming out. Okay, I'm going to react it with oxygen, which is O2, remember, because it's part of the diatomic families. Okay, where do you think I'm getting my oxygen from? Just right here, right? I'm not supplying more because we got enough. Okay, and we're going to make some carbon dioxide and water. Okay, what I want you to think about, and don't say anything out loud because I want everyone a chance to think and then we'll share, okay, is if these two things, I guess three things, okay, these need to somehow break and form to make these. Our last one showed it could happen in a single collision, right? One collision react into product. But if I were to Lego these apart by colliding and make those things, how many collisions do you think actually have to have happen? Don't say it out loud, just think. And then I'll let you share. Okay, but if like, once again, here's kind of to get you started, right? It was like, okay, the black needs to be connected to two reds. So somehow these have to come apart, these have to come apart, and then they have to attach. Think about that for a second while I do the demo. Okay? Okay, so for our demonstration purposes, I am going to bubble our methane into some soapy water. That way it catches the gas for us and doesn't just escape into the room. So keep in mind it has no purpose for the demonstration besides just to make it so we can like capture it before we react it. Okay? Eddie, I trust you.
Yes.
Will you come light a match for me? Okay. So I'm going to have a bunch of bubbles right here. When I say go, you're just going to touch the bubbles with the match.
Right.
But don't light it yet. Let's build it up a little bit. Okay, took off the watch. Okay, so bubble in some methane here. So once again, the methane is trapped inside the bubbles. The oxygen is outside the bubbles. Now we need them to collide, but we need them to collide with enough energy too. So that's what Eddie's role here is he's increasing our energy to make our collisions be successful. Okay? All right, go ahead, Eddie.
Whoa. That was pretty.
Can I try?
Not today, but maybe after the AP test.
That was nice.
That warm you up a little bit?
Yeah, that was good.
Okay, so we couldn't quite see our product because they're both gases in that lovely fire of a flame, right? Now show me on your fingers, what's your prediction? How many collisions have to happen for it to go from here to here at the molecular level? Take a guess. Show me on your fingers. What do you think? Take a guess. Nathan guessed 3. I see a 2. I see some more 3s. I see a 7. 6 over there. 7.
Oh.
1.
Wait.
Once again, I'm just trying to get your brain thinking here. I don't expect you to know the answer. Okay, the correct answer is this many.
Oh my god.
Oh.
So at the molecular level, a lot has to happen. Now, did it take very long for it to react? No, right? It's crazy. So these steps in a reaction, these hidden steps, right? The overall just says we start with this, we end with this, okay? But at the molecular level, a lot more actually can be happening that makes a reaction occur, and this is known as a mechanism. So our objective today is to understand how mechanisms work and how it fits to the overall reaction. Okay, the mechanism once again shows you, hey, to get from reactants to products, first, right, this bond would have to break. And then all these other things would be happening in the process. Okay? So as we're looking at a mechanism, and we call the different steps, we call them an elementary step. The key part of an elementary step is it focuses on, elementary thinking like simple, of a single collision. Okay, a single collision is happening in each step. If more than one collision is happening, then it needs to be broken down into 2 steps. Okay, so each step in a mechanism shows one collision. Now, the collision can happen between a variety of things, though. Okay? We have what is known as a unimolecular step, meaning only one molecule is involved. Which is kind of weird because in a sense then it's not really a collision because how does one thing, like what are they colliding with?
A different molecule.
But it's actually, that would make it not. So unimolecular is just one thing that just happens to break apart on its own. Okay, great example is our hydrogen peroxide, we said breaks down with light. Right, it doesn't actually have to collide with anything, but if exposed to light, it will break apart. Okay, if 2 things are colliding, and this is our most common, it's known as a bimolecular. Okay, so 2 molecules colliding with each other, bimolecular. A termolecular is 3 molecules, but it's extremely rare because you need 3 molecules that are all going to collide at the exact same time. Right, so imagine if Stephen and Mary each held one of these and I held one. Right, like what are the odds that we can all throw them at each other and all 3 of them hit each other at the exact same time? It's very hard for it to happen. They do exist, but those reactions are very, very rare. So just recognize, like, it shouldn't be your first guess, like, to be termolecular, okay? Here's some examples of how they look. Okay, so a unimolecular, once again, is just a single reactant, so just A here, turning into products. Now, once we've broken a mechanism down into its steps, you can write the rate law for each step by simply looking at the equation. So notice here, since my equation is just A to product, my rate law is just K, A, first order. Okay? On our next one here, okay, these are both bimolecular examples. Okay? So this one is 2A, so that's why it's bis, because there's two of them, even though they're both A. Okay? And then notice in the rate law, it's second order. So when it is a step, to get to the rate law is very simple. You simply look at the reaction and turn it into a rate law. But we can only do this because they are steps. They've been simplified down to a single collision. That's why we can do it. Otherwise, we have to use data like we just did on the quiz to find the overall rate law. Yeah?
How would you, like, what would be an example of a molecular reaction?
So it's like any sort of what's called just a decomposition. So a reaction like, so water, and once again, sometimes they obviously all require energy, but water can be broken down. Maybe this isn't the greatest example because that would be unbalanced, but it kind of gives us a start. But like it can be broken down if you send electricity through it and it just breaks apart the bonds.
Okay.
But in a sense, no collision between two things is actually happening. Does that make sense? Yeah, Mary. Oh, you're good? Okay. And then our last two, so with bimolecular, once again, notice two things, still bimolecular, just different. And then our last two here are just some examples of what a termolecular one would look like, right? You can have 2 in 1 or one of 3 different things. Okay? Notice once again that the 2 here turns into the order of the reactant. Yeah? Yeah, that would also be a termolecular as well, if it existed. Okay, let's try a few for some smiley faces here. So we need to identify the molecularity of each step and then write its rate law. So I'll do the first one, and then I'll have you do the other 3 for some smileys. So my first one, I noticed there's only one thing on the left, so it is unimolecular. And then my rate law would be rate equals K, and then since it's unimolecular, just N2O4 in brackets. Because only, remember, we don't ever put products in a rate law. Oh, by the way, there's a small typo. On the third one, scribble off that 2 there. It's not supposed to be there. Makes it not work. Okay, I'll give you 2 minutes. Talk it over with your table. Try this out for 6 smiley faces.
I got uni try by.
What?
Oh no, that's one. Yeah, it is the last one.
There's 2 NO.
The second. Yeah, bimolecular. And then the
NO squared. Okay, and this one would also be 2.
JV, do you
Yeah.
have to put rate equals before?
Yeah, rate law's kind of like the mathematical expressions we write.
Okay.
Yeah, the whole notation.
I remember what I was gonna ask. So is that just like fish soap in the bottle?
Dish soap and water.
Right.
Yeah.
And then
And then the methane got bubbled into it.
is that like always methane? Like that
Gas lines? Not always.
Do you have like a jug you could just like attach?
No, mine is hooked up to the gas line of the school, which is methane. But I'm saying other gas lines could be like your gas stove is typically propane.
Oh, right.
So, does that make sense?
Yeah.
Yeah, so there's like a gas line that runs. It's like the same gas line that like in the lab, like if when we use Bunsen burners,
Oh.
that will hook up to them. You just reminded me though, I should turn it off when I'm not using it.
It's not turned off.
Well, there's an emergency underneath thing. Because otherwise random students just come up and are like, hey, what's this do? And then like
I've done that before, but then I got really scared.
I
guess it's a good
that's why I keep it off.
Okay, got it.
Yeah. Yeah, because the school I did my student teaching at, I did at Cedar City. They told me a story of one time they came into the school on like a Saturday or something, and they could smell the gas line had been left on in the lab, but they were so worried because they don't know how long it's been pumping, so this room was just been pumped full of gas. So they didn't even want to like put their key and turn because any spark could like set it off. So they like went to a window and like very carefully like opened all the windows to like let it out so they didn't blow up their whole school. But
What kinds of gas are in the gas line that we
methane. Yeah.
Wait, so, like, how much would it take to, like, would it like, just explode the school or just set it on fire?
I mean, that room would, because it's contained in this, because explosions are just because you pressurized it, right? So you would get it in that. It'd be like the hydrogen balloon idea, but like whole classroom, you know? Okay, check your answers with mine. For smiley face, question, Will.
How pressurized would the room have to be to explode?
I don't know. Versus just like fireball. Yeah, I'm not sure. I haven't done the math on that. Okay.
Figure that one out by experimentation.
Should we test it?
Yeah, we
Okay, this one, have a smiley face if you said it was term molecular. I'm going to go down the columns, then we'll go to the rate laws. This one you should have said is bimolecular, and this one is also bimolecular. Have a smiley face for each. Questions on molecularity? All right, and then our rate law, you should have rate equals, don't forget your K, NO should be squared, and then O2. Have a smiley face. Questions on that one?
put like the gas part in parentheses?
Nope. Yeah, good question. Like, are you saying that they're gases?
Yeah.
Nope, you don't have to. If you did, it's not wrong too. Just more information. So, yes, Marilyn. Yep, it's just because when it's a step, the order matches the balanced equation. So since there's a 2 here, that just becomes the order there. Does that answer what you're asking? Okay. And then this one you should have rate equals K, CO, and NO2. Like so. Questions on that one? And then our last one, rate equals K, NOCl squared. Questions on our steps here? Okay, coming back to our demo we did, okay, can I simply say for this reaction then that the rate would be K CH4 O2 squared. Give me a thumbs up or thumbs down if that is valid. Thumbs up yes, thumbs down's no. Just looking. Okay, Lila, you didn't fail me. Lila, it is no. Why is it no?
Tell how fast it goes by looking at it.
This is an overall reaction. You can't write a rate law from an overall reaction. You can only write it for steps. So steps, you can go from the step to the steps rate law. But you can't go from an overall equation and say, oh, its rate law must be this because of the balanced equation. Does everyone see the difference between the overall? What would I have to do or need to find the overall rate law? I need data. I need the steps, right? I need what's happening to then get to the overall. Good? Yes, Ray?
So like the question tell you that it's a step?
Yep. Yep, so it would let you know, like, once again, like this is the overall reaction, or like these are the steps of the reaction. So one key word is that word like elementary, right? They'll talk about like, hey, this is an elementary step, which means it's not the whole thing. And honestly, for the most part, you're never going to see steps without other steps. Like they're never just going to give you step 1, they'd give you step 1, 2, 3, however many steps it needs to be. But what you will see a lot of are overalls, right? Like that's all we've seen all year are just overall reactions. So does that make sense, the difference? Yeah, good question. Okay, so as we look at our steps and as we talk about collisions, let's just emphasize what we kind of mentioned. The two things that need to happen. So you have to collide in the right orientation. If it doesn't collide in the right way, it just is bumper cars or you're making something you weren't planning on making. Okay, so you have to have the right orientation of the molecules so that the new bonds can actually form where they need to. Okay, once again, this is another reason why most collisions are not successful, is because there's really only one place that makes the reaction happen. All the other collisions aren't where it needs to be. Okay? Say that again. It's part of it, yes. Yeah, we'll get into that next 2 times I need. The other thing that's needed, so we need collisions with the right orientation and enough energy. If they don't have enough energy, then it doesn't matter because they just bounce off each other, right? So that was Eddie's role in our demonstration, is he provided what is known as the activation energy, the energy needed to activate the reaction. It's the same thing your car does every time you turn your key, is you're sparking it to get the activation energy to start. Okay? The catch is with activation energy is once it's supplied, you don't have to keep putting it in. Right? Like if I had more and more bubbles, Eddie wouldn't have to keep putting matches in. One match would let them all go. Okay? The other thing to recognize is it's just a minimum. You can give more, right? You can pay more energy and it will still go. But if you don't pay the minimum, then the reaction can't happen. Okay? Let's take a look at some graphs we've seen before, and then we're going to look at a new type of graph today. Okay, so we saw these graphs back in Unit 3. Can anyone by raise a hand remind us what this graph, this Maxwell distribution for gases is showing us? Can someone remind us? Go ahead, AJ.
It's showing us the speed of essentially each molecule, so or the average gas. So you have a majority of molecules in the center, and then the faster ones are on your side.
Good, right? So this dark blue is for helium. So helium molecules, right, can range in speed from way up here to way down there, and on average, they have this speed, right? So this first graph is a reminder of how size changes distribution, right? Things that are small have a much wider distribution than heavier molecules. Okay, so keep in mind, like AJ pointed out, when we read these graphs, we're kind of looking at the area underneath the curve. Okay? That's what you're looked on, is that whole area represents all the individual molecules. Okay? All right, let's take a look at this next one here, kind of keeping that same mind. Okay? I'm going to use 2 different colors if you want to highlight with me to emphasize. Okay? So we have this dashed line, which we're calling, I covered T1, and then the solid line, which is T2. Okay? Don't say anything out loud, but for a smiley face, based on what that graph is showing me, which one is at a higher temperature, T1 or T2? Don't say it, just think it. Based on that graph and what we've known and talked about, which one is at a higher temperature, T1 or T2? All right, on the count of 3, show me on your fingers which one's higher. Ready? So show me a 1 or 2. 3, 2, 1, go. Showing me a 2, have a smiley face. You're correct. So keep in mind, as temperature goes up, what's going to happen to kinetic energy? Yeah, kinetic energy is going to go up. And so if I look at this graph here, my solid line, if I highlight everything under that curve past the activation energy, there's more molecules at a higher speed. Everyone see that? Versus just the pink area shaded in, right? There's less molecules. So it gets more distributed because they're going faster. This E of A, that is our activation energy. That's the symbol we use. E for energy, A for activation. Sorry, I'm still getting my handwriting down with this pen. Sometimes it doesn't look the greatest up there, but maybe it always looks that way and I just don't know it. Yeah, Marilyn. Yes, very good. So at temperature 2, there's more molecules with enough energy now to actually turn to product. So once they've crossed this E of A barrier, they now can react. They can now change to product. So this kind of shows you that connection between temperature we mentioned and our activation energy. Okay? All right, here's our new graph. Yes, Mary?
What is the minimum energy required to initiate additional reaction called?
The activation energy. All right, this right here is known as our reaction pathway diagram. I think of it as it's the story of the energy from start to end. Okay, so not all graphs you read this way, but this graph you will want to read from left to right to see the story. Okay, the y-axis is our energy value. Okay, so energy high, energy low is the y-axis. The unit we'll typically see is the unit of a kilojoule, kJ. I don't think we've been introduced to kilojoules yet. Have we this year? Have we seen them in I didn't think we should have. I just sometimes lose track. So unit 6 is all about energy, so we'll really dive into kilojoules. Just recognize a kilojoule, so that's what it stands for, right? It stems from the unit of a joule. So a joule is a type of energy unit, and you can connect it to any other energy unit that maybe you're more familiar with. So one you're probably most familiar with is the energy unit. Doesn't help us because there's none in here, but the energy unit of a calorie. So if you look on a nutrition label, calories are a unit of energy. They're the unit we use to measure what our body needs, right? So when you look on a nutrition label, it tells you in calories. If you get a candy bar from England, it will actually tell it to you in kilojoules because you can convert between them. Okay, we could convert kilojoules into voltage. So voltage is another type of energy unit primarily used for battery and electrical things. But once again, it's just the same as in mass, right? Mass can be measured in pounds, tons, grams, all different units, but they represent mass. So for energy, we can do calories, kilojoules, volts. What's that? I should have said weight, not mass. So, yeah, Layla.
Is this graph strictly endothermic, exothermic?
Yes, and so if you've taken chemistry before, we saw these with endo and exos. Yep, and so this will connect into Unit 6 again. That's when we'll bring up those topics. Yeah. Cameron, then Mary.
How many calories are there in kilojoules or
Oh. Don't quote me on this. It's in a joule to calorie, it's 4 point something something. So kilojoules actually, it's 1,000 difference more. So it looks like you're eating a lot more because you eat things in the 10,000s versus ours is based off a 2,000.
So there's more joules in a calorie than there are calories.
Yes. Yeah. Does that answer your question?
Yeah.
Mary?
Could you also convert from kilojoules to watts or temperature?
Temperature's a little different. Temperature connects into kilojoules. It's connected to it, but Fahrenheit isn't a unit of energy. So temperature isn't a straight up unit of energy. Mm-mm. So temperature is purely a measure of it is based on I don't know how to explain this right now.
Energy?
But there's different. It's a kinetic energy measurement, not a heat energy measurement. So maybe think about it that way. Kilojoules is a heat measurement energy, which is different than a temperature.
Wait, but temperature is a heat.
So heat is used to calculate kilojoules, but it's not the same. Something with 20 kilojoules isn't at 20 degrees Celsius. They're not the same, but they are correlated to each other. I don't know how to better explain it right now, but I will keep thinking. Once again, Unit 6 is all about heat and energy, so I'll see if I can come up with a better example for that. Yeah, Seth.
I googled it. 1 kilojoule is equal to 239.0057.
So 1 kilojoule is that many calories. So, Thanks, Seth. So as we look at this graph, once again, first line represents the reactants, right? Reactants come with a certain amount of potential energy inside of them. So before we did our demo, we had this and we have this, and they have energy inside of them. Okay, their energy together represents this line. Okay? What had to happen for the reaction to occur?
More energy added.
We had to add a kickstart, right? That's why it goes uphill. All reactions require some amount of kickstart. Not always a flame. Sometimes the room just has to be warm enough and it will go, right? But it has to have some amount of activation energy. So this difference between where you started to the peak is the activation energy. Be cautious here. It is not, I'm going to draw a line, that's not activation. It's not from the bottom to the top. That's not activation energy. It's from where I started to the top of the peak. Okay? Once we get to there, I think it was kind of like a roller coaster idea, right? We put in the energy, and then energy comes out, right? Doesn't take any energy to go down the hill. And this represents the energy that the products now have. Okay? The difference between where I started to where I ended is the overall change in energy, which is known as delta. So remember, delta is change. Triangle means change. Change in enthalpy is its name. But for now, just recognize it as it's the change in overall energy. We'll dive more into enthalpy later. Yeah, Will?
Are products ever hydrogen reactants?
Yes, they could be. So let's write our two scenarios down here. So in this graph, the reactants have more energy than the products. Right, so the reactants were higher than the products, which resulted in energy released.
Taylor is checking out.
Okay. Versus what Will just brought up, if the reactants have less energy than the products, then that means energy has to be absorbed, right? Which we'll get into as our endothermic reactions, right? Energy is needed to be supplied in order for it to happen. Yeah, AJ.
So if an endothermic reaction is taking up energy, does it potentially like cut the activation energy short so it doesn't finish its reaction? What do you expect for all molecules?
So yeah, if I'm understanding what you're asking, so with a reaction where you have to supply energy, that energy has to be continually supplied in order for it to get all the way over. Otherwise, if you stop, then you would stop making a product in the end. Is that what you're kind of saying? Yep. Yeah. Yeah, Marilyn. What do you think? Yep. Because those ones can often just happen on their own, right? Like, we don't have to put it, they might need a spark, but then they'll keep going on their own. Endothermic, or the ones that absorb energy, like it has to be put into it, so they're way less likely. Yeah. Will, and then Marion.
So batteries would be absorbing energy then, like rechargeable?
Good, yeah, so rechargeable batteries do both. While they're working, they're releasing energy, and then while you're charging it, it's making it go backwards on the graph to stock it back up. Yeah, exactly. Miriam.
So, cooking meat is like an endothermic reaction?
Yes. Yes. Yep, because you're having to put it in, and if you take it off, it's not going to keep happening, right, if you take that heat away. So, yep. You take it off, and it just keeps cooking.
It's just a hand warmer.
For like a second, you put it in, and it just finishes cooking on the stove.
Now, that would be something, huh?
Wait, no, you just eat it and then you.
Yeah, you just, like, kickstart it, and then popcorn bag just starts popping up on its own. Yeah.
If that were the case, you wouldn't want to cook it because then it would end up with less calories.
Yeah, I don't know about, but still, if there's some way to make it happen. Yes, Mary?
So is photosynthesis an endothermic or exothermic reaction?
What do you think?
Is it endothermic?
Why?
Because grass is cold and asphalt is hot?
Not quite, but what has to happen for photosynthesis to occur? What does it need?
Light?
Yeah, so that it has to take energy in. Yep.
So it is endothermic?
So it's endothermic, because without the sunlight, it won't happen. So that's its source of energy that it's taking in.
Okay.
Yep. Okay, let's try a question for some smiley faces here with your table group. Tell me, between these three graphs, label each graph as releasing energy or gaining energy. And then second, rank them from slowest to fastest, assuming that they're happening at the same temperature. So once again, if I started them all at the same time, rank them fast to slow. You can use, they have little numbers underneath them, 1, 2, and 3. You can use those to answer, okay? All right, talk with your table group. Ready, set, go.
This one, I think it's 2, 1, 3 because of
This is yours, Rachel. I found it on the ground.
It's not mine, no.
Lila, is this yours? You always write in pen. Okay, I just found it on the ground. I'm going to put it in the random jar.
Is that like is that the overall change?
Because it has number 1 goes faster. It has more.
Is it like, how they to scale with each other as far as like x-axis time goes?
Yes.
All right.
Yes.
Well, then 3 would be the fastest.
It also, if you know, it kind of gives you the values of like the numbers a little bit. That can help. Yeah.
How do they see?
What's that?
Wait, Sean looks up from his computer.
No, I just put it in that jar.
Okay, great. Because my lid just broke.
Oh my goodness, that's like a sign. Fell from the sky.
How do we tell if it's faster or slower?
How do you think?
I have no clue. Is it like, because they're all like the same length.
Okay.
Does that have something to do with like the UV? Okay.
Put 3 cross-country runners at the bottom of each hill. They're running the same amount of energy. Who's gonna take the longest to get to the top?
It's gonna be like 2, 1, 3.
Okay, ready? You should have said released, gained. Have a smiley face if you identified that for part 1. Questions on that side of it? Normally that one people are okay with. Okay, now let's talk about their speed of them. You should have identified that 2 will be the slowest reaction to occur, followed by 3, and then 1. When it comes to the speed at which a reaction occurs, it's all about the uphill, the activation energy. Downhill's like always instantaneous. Doesn't make a difference. But this one has the biggest uphill, so from start to top, 25 kilojoules. This one from start to top is 20 kilojoules, but this one's only 15 kilojoules. So 1 would go the fastest, 2 would go the slowest. Questions on that? Yeah, Layla.
Would that vary with like the amount of energy that you're putting in?
Yes, so that's why it's specified, assuming they're all happening at the same temperature.
Okay.
So if they're all at the same temperature, meaning given the same amount of energy, that's what we would see. Does that answer what you were asking? Other questions on that one?
Wait, so what is that measurement from the original energy to the like peak?
Yeah.
Isn't that just like how much energy it takes to start it?
Yep. And once it's started, it just goes. Does that make sense? And so if it costs more to start it, it's going to take longer to get there.
Okay.
Does that make sense? Yeah, AJ, then Will.
For endothermic reactions again, do they all need to hit the peak as well? Because exothermics, they're releasing enough energy usually that I can actually.
Yes, they can kind of fuel themselves to keep going.
For endothermics, do you constantly need to have like in that example, you constantly have 20 kilojoules per mole in order for it to continue going.
Yep.
So you can't just reach that peak and then you can just drop the temperature to whatever the new energy is.
Yep, and it wouldn't go. Yeah, but it's a good observation with like the exothermic ones is because they release heat in the process of it, they then kind of fuel themselves to keep going. So yeah, good observation. Will.
After repeat, does it not matter how much energy that has to go to get the product? Like it's all the same.
It's in terms of what we can measure, seems instantaneous.
What is something that has more energy for number like using faster? Like how if you have one log of wood and you burn it, as
Yeah.
opposed to like a bunch of wood and you burn it, then the bunch is gonna burn faster than just the one. There's more energy in it.
The logs burn even like if you have more like tinder and stuff, then that burns
Yeah,
faster.
hotter burns it faster.
Because you're saying it will help like fuel itself. The thing to keep in mind, and this will once again kind of fit in the next unit as well, we're measuring in like molarity per second. So it's a ratio of amounts. So even if you have more of something, in terms of its rate of change, right, it's like consistent. Because molarity is like moles per liter of the substance. Does that make sense? So you're like taking that into account of how much energy is coming out. So just like amount for amount, like the rates would be slow to fast in that order. Does that kind of make sense? And once again, it'll kind of when we get into Unit 5 a little bit. Okay, let's get back into our final thing to get with mechanisms here. Okay, ignore this. We're going to solve this. Pretend that's not there. You didn't see anything. Good. It's not supposed to be. Okay, our goal here is to connect mechanisms to the overall. So what we want to identify is what are my actual reactants and actual products versus kind of these in-between things that may be used in the process. Can anyone by raise a hand see something in these two steps, so step 1 and step 2, that we wouldn't say is an actual reactant or product? Miriam.
In the last product set, should it just be NO2?
No, this one should be NO2. I know, we're using these chemicals a lot today. Good observation, though. Anyone see a molecule? Yeah, Rachel. Why would you say CO?
I don't know, because normally we just hear like CO2.
It is a more, it's carbon monoxide. It's the one you don't want to breathe in. But we are going to keep that actually as a reactant here. Let's see, what do you notice? Have a smiley face though, Rachel, for trying.
How did we get the extra?
So keep in mind, this is showing us steps of an overall, okay? So it's saying step 1, this collides with this, making NO3 and NO. Step 2 is then NO reacts, no that doesn't, NO3 reacts with CO to make NO2 and CO2, okay? So notice here, everybody, circle this with me. Notice in step 1, we made NO3, or the reaction made it. But then what happens to it in step 2? It got used, right? So it was made and then used up, which means it's not a reactant or a product. So we're going to take that out from the overall. It was part of the steps, but in terms of the beginning and the end, it's not there. Anyone see anything else that we can maybe cancel away in a similar fashion?
We have an NO2.
Good. What do you know about NO2, AJ?
It's a old, I guess, product and material.
There you go. So we started with NO2 and we ended with it. What do you call a substance you put into reaction and it comes out in the end? Ooh, close.
Spectator.
It's like a spectator, but something else. Maybe helps the reaction go.
Catalyst.
It's a catalyst, right? Catalyst we put in, and then they still come out, okay? So let's write our overall, and then we'll label these two things, okay? So what I'm going to write is just what's left. So we'd have NO2 as a gas, reacting with CO as a gas, turning into NO and CO2. So everything that's left is our actual overall reaction. So this is my overall. Label that as your overall reaction. Where the things on the left, these are my reactants. And these are my products. Questions on how I went from the steps to the overall? Yeah, Stephen.
So is it one of the NO2s a catalyst or is it both of them?
In a sense, it's just because it's the same thing, right? Like, it's not really two of them. It just, because it was in the reaction, but then it comes back out of the reaction. So let's label that one. So make sure you label NO2 is a catalyst in this reaction. And NO3, what was different about NO3 versus NO2? Because they both got canceled out, but what was different, AJ?
It was like an in-between step that wasn't there before and wasn't there after.
Oh, I should have paid you for the use of that word. What was the first word you said?
In between.
And it's called an intermediate, is what it's called. So intermediates are substances that get made in between steps. They help in the collision process, but they're really not there in the end. Questions on any of those new labels? So our overall, and then our catalyst and our intermediates. Yeah, Matthew.
I don't really understand why you're able to
Cross off which one?
the ones you crossed off.
So the idea for an overall reaction, going back to the beginning, should just show us, so like back at the beginning, this was an overall, right? What are my reactants and what are my products? The mechanism step shows us all the in-between things that are happening to get there. So that's why we don't show them in the overall, we don't show intermediates, we don't show catalyst, because they're not really, I guess they're just not part of the big picture. And so in the overall, they're no longer shown. But the catch is, let me go to this next one, intermediates can be proven. So mechanisms come from data. They're not just some random thing a scientist said, hey, I think maybe this happens and then this happens. It could start that way, but then they go and prove it. And they do a reaction and they actually are able to isolate intermediates. So this graph right here is for a two-step mechanism. So the more steps we have, the more exciting the roller coaster becomes. Because every step has its own activation energy. So this would be step 1, and then this would be step 2. And the more steps you have, the more exciting the roller coaster really becomes. Yep. Okay, questions on that before we try a practice problem? Oh, we have 1 minute. Oh, I gave you the answers. Don't look. I don't know why I'm cutting my iPad. That doesn't help. Okay, try this one super fast. Okay, try example 5.7a. See if you can tell me what are the intermediates, what is the catalyst if there is one, and what's the overall reaction. This is similar to what your homework will look like tonight. So your homework is there's one worksheet that deals with the graph things, and then 2 AP classroom quizzes. Should be pretty, like homework should be really fast. Someone from A3 stayed during lunch and they said they got all the homework done in like 15 minutes. Oh, perfect. Yeah, it's quick, so at least I think so.
The homework tends to be quick?
It should be. It should be. If you want to check yourself, don't look until you're done, but the answer's on the board. But don't look if you're not done. Sorry, if you say don't look, then everyone looks.
Christian Quinn and Brighton Law, come to the front office, please. And students, if you are parked in the range parking lot, they are going to be starting range driving in just a few minutes, so you need to get your car moved out of the range parking